So similar to the last problem, what we're going to do is we're going to find P1, P2, P3, P4, and P5, the 5 Taylor polynomials that correspond to this time the natural log of x centered at a equals 1. All right, so what we did last time was we started by making a table of derivatives. All right, and remember, we're going up to 5, so we have 0, 1, 2, 3, 4, and then surprise, 5. And we're just going to find successive derivatives of the natural log. All right, and we're going to approximate the value of ln of x centered at a equals 1, which we know to be 0. All right, but let's see how good of an approximation that we can be able to get to those polynomials. Okay, so next thing we have to do is we have to find the nth derivative, okay, of the original function. And so remember, the original function is always going to be the 0th derivative. We know that the first derivative of ln is 1 over x, which is the same as x to the minus 1. And we're going to keep it like that as we find the successive derivatives. Next derivative is going to be minus x to the minus 2, which is the same thing as minus 1 over x squared. Third derivative is going to be 2x to the minus 3, okay, which we're going to write, as 2 over x cubed. And next one we're going to get is going to be negative 6x to the minus 4, or negative 6 over x to the 4th. And then finally, for the last one, 24x to the negative 5th, which is going to be 24 over x to the 5th. All right, so last thing we're going to do is we're going to substitute the value of a back in. All right, so this is going to be fn at a. Okay, remember that a is equal to 1. And so when we substitute 1 back in for x here, that just becomes the ln of 1, which is 0. The next one is going to be 1 over 1x, which is 1 over 1, which is 1. The next one is going to be negative 1 over 1 squared, which is negative 1. And we're going to hold on to these, okay? So let's just box these and hold on to them. Okay, so because we are going to need these to be able to find a Taylor polynomial. And then we're going to graph it just to see how good of an approximation we can get. All right. Next one is going to be 2 over 1 cubed, which is going to be 2. Next one is going to be negative 6 over 1 to the 4th, which is negative 6. Right. And then finally, we end up with 24 over 1 to the 5th, which is 24. Okay, so these are the coefficients or the f double or the nth derivative at a. All right, so now we can go ahead and remember our formula that we're going to use. Okay, we're just going to keep substituting the values of the derivatives divided by n factorial. Okay, so for p sub 1 of x, now remember, p sub 1 of x is going to be equal to f at a plus f prime at a x minus a. All right. And we know that f at a is going to be 0, f prime is 1. And so this is going to be equal to 0 plus 1 x minus a, or x minus 1 in this case. Excuse me. So we wind up with x minus 1. Okay, so remember this time a is equal to 1, so it's not going to be x minus 0 for us. Okay, so that's p of 1. Now for p of 2, remember that's the original, or what we just had for p of 1. So remember our pattern. Okay, it's going to be f at a, f prime at x minus a, and then we're going to have a second derivative at a divided by 2 factorial x minus a squared. So in this case, we're just going to copy down the x minus 1, because that's what we just found, plus, now we're going to have the second derivative, which is going to be negative 1. Okay, so remember, if we draw, and let's make sure that we understand where each of these lies. Okay, so I'm just going to try to draw like a grid here, so that way we understand where that 2 matches up to negative 1, and third derivative matches up to 2, fourth derivative to negative 6, and then fifth derivative to 24. Okay, so this is going to be plus our negative 1 that we just got. okay, for the second derivative. That's going to be minus 1 over 2 x minus 1 squared, okay? Or another way to write that, x minus 1 minus a half x minus 1 squared, right? And of course, we could FOIL that out and get something a little bit better, but we don't have to, okay? For P3, it's going to be what we just got, okay? So I'm just going to copy that down. So it's going to be x minus 1 minus 1 half x minus 1 square. And then since we're on the third derivative, that's going to be plus f triple prime at a divided by 3 factorial x minus a cubed. All right. Or in other words, we know f triple prime is going to be 2, right? And we know that 3 factorial is 6. We know that a is 1. So another way to write this is x minus 1 minus 1 half x minus 1 square plus, okay, so remember f triple prime was 2 right here. So that's 2 over 6 x minus 1 cubed. And we know 2 over 6 is just a third. So that's 1 over 3. And remember, to get 6 out of this, remember that's 3 times 2 times 1, which is 6. Okay, so this is our third degree Taylor polynomial. Okay, and technically it's P3 at x, not that it matters too much. All right, but since that's how we defined it, let me go ahead and do that. Okay. So then for our fourth order Taylor polynomial, which I'm going to call P4 of x, that's just going to be the previous. So x minus 1 minus a half x minus 1 square plus a third x minus 1 cubed. And then we're going to take the fourth derivative, which is negative 6. So it's going to be plus negative 6 over 4 factorial x minus 1 to the fourth. Okay. Now we know that 4 factorial is going to be 4 times 3 times 2 times 1, which is 24. Right. So this is going to turn into negative 6 over 24. And we know that that's just going to be negative 1/4 if we simplify that. So all of this coefficient just becomes a minus 1/4. All right. And then finally, we can get to P5, which is going to be the exact same thing we just got, except now we're going to take the fifth derivative and divide it by 5 factorial. Okay, so remember, fifth derivative is positive 24. So P sub 5 of x is going to be x minus 1 minus 1 half x minus 1 square plus a third x minus 1 cubed minus a quarter x minus 1 to the fourth plus, we just got 32, 5 factorial, and then x minus 1 to the fifth. All right. Now, 32 over 5 factorial, 5 factorial is going to be 5 times 4 times 3 times 2 times 1, which is 120. Right. So this really winds up being 32 over 120. And of course, we can use our calculators to simplify this. Okay. And I do believe that 32 times 5 is going to give us 120. So I think this is going to simplify into, oh, it should be 24. I'm sorry, not 32. I copied the wrong number there. So this should be a 24. All right, so sorry about that. All right, I was wondering why it wasn't going to be a fifth, which it should be. But notice this fifth derivative is 24. So 24 over 120, I believe that 5 times 24 is 120. So this should simplify into 1/5. All right. So these are our 5 polynomials, okay? And remember, each of these is supposed to represent the natural log of x around the point a equals 1. All right, so let's see how good of a job these polynomials do. Okay, so I'm going to go back to our graph. All right, and I'm going to plot all 5 of the polynomials, including the natural log of x. So here's our ln of x function. Let me get rid of this and this and this. Don't need them. All right. Remember, our first order polynomial was x minus 1. Not so bad. Okay. So if we look at that and we zoomed in around 1, it's somewhat viable. Okay. But as we zoom out a little bit, it's not as viable. okay? Then we had x minus 1 plus 1/2 x minus 1 squared. All right, so a little bit better, okay, as we look around here. All right, but it's still about the same, all right, as what we had before, okay, for the natural log function. So especially for the linear part, okay. And again, all I'm doing is I'm just substituting these values back in. That should be a minus 1/2, excuse me. So when I go back, this should be a minus 1/2. Okay, so that looks about the same as the linear. In fact, it's actually a little bit better. Okay, for the natural log function. Okay, still not all that great. All right, I'm going to copy this, and the next one we had was plus a 1/3 of x minus 1 to the third power. All right, so starts getting a little bit better. Okay, as we get a little further out. Okay, remember we're only trying to model it around 1. Okay, so all of these do a pretty good job around 1. All right, but ultimately we want them to really do a good job of just the natural log function. All right, next one we had was minus a quarter. Okay, so we're going to say minus 1/4 of x minus 1 to the fourth. All right, and that does a decent job again. Okay, it's a little bit better than the cubic that we had. Right, and then the last one that we had, I'm just going to copy this. And we're going to add a 1/5 of x minus 1 to the 5th power. All right, so as we increase the order of the polynomial, it looks like it's getting a little bit closer, okay? So let me get rid of some of these earlier ones. All right, and as we can see, like, the 5th order does a decent job, especially around 1, okay? Because that's what we're really looking at is as we stray further from 1, it starts modeling it not so poorly, okay? So for a natural log function, at least towards infinity, but here it starts to become pretty evident that there's a lot of error, okay? So that's our Taylor polynomials, all right? So this is how we're going to go ahead and try to compute these Taylor polynomials. And of course, we could do higher than 5th degree if we wanted to. In our last videos, what we're going to do is we're going to find some Taylor polynomials and then approximate what the values are going to be from those Taylor polynomials around a point, and then we're going to figure out what the error might